Before we continue on, we need to discuss um, the origin of light or the nature of light. Remember, light is an electromagnetic wave. It's part of what we call the electromagnetic spectrum. Here we have a view of the spectrum. As was mentioned in prior time, either this course or before, the electromagnetic wave spectrum includes radio waves, microwaves, infrared, visible is the actual light we see, ultraviolet, X-rays, and gamma rays. That whole spectrum of waves is what we call the electromagnetic waves. And if you think about it in terms of wavelengths, as a reminder, radio waves are somewhat the size of buildings, and then when from the size of buildings to the size of humans. Microwaves are about 1 centimeter in size, so the size of a bee. Infrared, we go to pinhead, very tiny for the wavelength of visible light. It's about a few hundred nanometers. And ultraviolet, it becomes the size of molecules, X-rays the size of atoms, gamma rays the size of nuclei. Okay, now, what does it mean to say electromagnetic waves? So if we have some kind of a generator that allows charges to move up and down a conductor like this. So I have positive charges up, negative charges down, and we keep the charges moving up and down. So what that's going to do is generate an electrical field. Anyway, every time we have a charge, we have an electrical field associated with it. We'll get to that as a different topic, but that if the charge is going to change, if it's going to move, that electrical field is going to change. And the change in electrical field, that's what's going to travel. And it's going to travel in a direction perpendicular to the direction of the change of the electrical field. And here we have the electrical field changing up and down. The wave is going to travel sideways. Now, just one quick question here. For example, when we transmit electromagnetic wave for TV or radio transmission, if this is the antenna at the station, how should you orient the antenna of your TV or radio or whatever? Of course, if the wave is coming directly to us, if it is not being reflected off multi-surfaces like walls, trees, whatever, before it gets to the TV, then our antenna should be oriented the same direction as the antenna of the transmission tower. And that's because when the electric field is going to reach the antenna, it's going to be along the vertical. So when it meets the antenna along the vertical, we are going to get maximum electric field affecting the antenna, and we get a better signal. Now, one thing to note, and that's why we call it electromagnetic. Electro is for electrical field, magnetic is for magnetic field. Now, whenever we create an electric field, a change in electrical field results in a change in magnetic field. So the generator is actually creating both an electrical field and a magnetic field. And they are, as you notice here in this graphic, they are in sync, but then they are perpendicular to each other. In this case, we have the electrical field oscillating along the vertical, the y-axis here. The magnetic field is oscillating along the horizontal, the z-axis here. The wave is going to travel perpendicular to both of them, which is the x-axis here. So now, because of that, the wave is, the electromagnetic wave is what we call a transverse wave. The oscillation is perpendicular to the direction of travel of the wave. That's transverse wave. Oscillation, either way you look at it, electric field oscillation or magnetic field oscillation, either one of them is happening perpendicular to the direction of motion of the wave, which is the x-axis. Now remember, longitudinal waves, example of longitudinal waves, you have sound. In sound, the oscillation, for example, is going to happen in this direction and the wave is going to travel in that same direction. The other thing that you need to remember, the electrical field and magnetic field are always perpendicular and they are always in phase, meaning that E and B increase and decrease at the same time, not out of sync. They are always in sync. Now, the other interesting thing that took humans a long time to figure out and understand, electromagnetic waves travel in empty space. They can travel in empty space. When they travel in a medium, they're going to travel at a slower speed, but they travel in empty space. Remember, sound waves, for example, cannot travel in empty space. The speed of light in vacuum is what we call c, and it is 3 × 10⁸ meters per second. Now, don't worry about this. We'll get to it later on. So it is 3 × 10⁸ meters per second in vacuum. It is lesser in other media. The 3 × 10⁸ in miles per second is 186,000 miles per second. If you'd like to find how many miles per hour, just multiply that by 3,600 seconds, and so you'll get an even larger number. Now, the other thing that you need to remember is the relationship between frequency, wavelength, and speed. It's the same relationship as for all types of waves. The only difference here is if we are in vacuum, the speed is going to be c, but f is going to be the speed of the wave over the wavelength. Okay, now which of the following waves are transverse waves? Okay, light, it's an E&M wave, so it is transverse. Radio, it's an E&M wave, so it is transverse. X-ray, it's an E&M wave, so it is transverse. Microwave, it is also an E&M wave, so it is transverse. I should not have included those. I'm not going to include those. Water wave is a little bit more complicated than just a transverse, so that's why I should not include it. Now, the wave that's for surely longitudinal is sound, and obviously it's not transverse. Okay, a quick thing. Now here we have shown the electrical field of an E&M wave that is broadcast at a 96.1 megahertz. So 91.6 megahertz, that's the frequency. So 96.1, 10⁶ hertz. The question is, what is the direction of the magnetic field? Obviously, it's going to be perpendicular. So it's going to be like this. So the wave is traveling along the x, this is y, so it's going to be along the z-axis. Okay, now it is asking us to label the two tick marks here. Now, how do we need to label them? This is the x-axis, so the separation between them is a wavelength. So we need to find the wavelength. Remember the equation that we just have here. So F is equal to C over lambda. So F is equal to C over lambda. So the lambda is equal to C over F. So it's going to be 3 × 10⁸ meters per second over 9.6 10⁷ hertz. So 3 × 10⁸ divided by 9.6 10⁷. So I'm calculating this on the side. 3 × 10⁸ divided by 9.6 10⁷. So we get 3.1 meters. So this first tick is going to be 3.1 meter. The second one is the second wavelength, so it's going to be twice that, so 625 meters. You know, I carried in more digits than I showed here. Okay. Just another reminder, change in B creates E, change in E creates B. We'll get to that later on. They have a relationship between them. They are in phase. Remember that. Okay, just I put there the relationship, but we'll get back to that later, so it's not very important right now. Okay, let's see this question here. Suppose that the electrical field of an electromagnetic wave decreases in magnitude. What happens to the magnetic field? That's the key. That's what we are trying to get. It decreases. They are in phase. Whatever happens to the electrical field happens to the magnetic field, and vice versa. Okay. Now, what I'm going to do, I'm going to try to show you this in the form of simulation, kind of showing you this in action. I pulled up the simulation like it would appear if you go to it on the website. Okay, now I would like to manipulate it a little bit, so I'm going to rotate it. In this case, we have the z-axis up and down, the y-axis sideways, and the x-axis along the horizontal. Initially, the electrical field is set up with both a y component and a z component. I'm going to kill the y component. Okay, so it's along the z, and then I'm going to tell it to show me as well b. Okay, and I'm going to run it, and that's what we have. You see, as the wave is oscillating, that's now the magnetic field is oscillating along the y, the electrical field is oscillating along the z, and then the direction of motion is along the x. That's what we are seeing. Okay? And the speed is, as we said before, it is c.